Hello everyone, my name is Shen, currently a PhD student at Peking University. In this talk, I will introduce our work titled EarFisher Detecting Wireless Eavesdroppers by Stimulating and Sensing Memory EMR. This is a joint work with my PhD advisor, Dr. Huang. Because of the broadcast nature of wireless channel, eavesdropping has been a fundamental threat to wireless security. To date, the primary countermeasure has been encryption. However, to facilitate open access, wireless networks serving public areas like the airport and campus typically have Layer 2 encryption disabled. Even when encryption is enabled, attackers may decipher the encryption key by analyzing side channels produced by timing information, power consumption, and so on. Furthermore, encryption protocols themselves often suffer zero-day vulnerabilities. For example, recent researchers uncovered that WPA2 is vulnerable to the key reinstallation attack. The flaw has been present for more than 13 years before being discovered, orthogonal and complementary to prior encryption solutions. In this work, we explore the feasibility of detecting the presence of wireless eavesdroppers. Prior solutions rely on sensing RF signals leaked from receiver circuits. However, such leakage is extremely weak, limiting detection range to only a few feet. More importantly, because all wireless radios emit leakages during receiving, this method cannot differentiate eavesdroppers from legitimate receivers. To overcome these limitations, we leverage a key architecture-level insight. As shown in this figure, a wireless receiver typically consists of a memory, a CPU, and a network interface card, or NIC. A legitimate receiver decodes signals in NICs, and then checks the receiver address of the packet. If the packet is destinated to other devices, it will drop the packet in NIC. In comparison, an eavesdropper will transfer all packets to memory and process them using CPU. This gives the detector two key opportunities. First, the eavesdropper will emit electromagnetic radiation, or EMR, from memory bus when transferring other devices' packets. Second, compared with RF linkage of receiver circuits, Memory EMR is relatively stronger due to the multi-channel architecture of modern memory, which amplifies EMR and thus allows for longer sensing range. Exploiting these two opportunities, we designed EarFisher, the first system that can detect wireless eavesdroppers from a long distance and differentiate them from legitimate receivers. As shown in the figure, EarFisher consists of a stimulator and a detector. The stimulator sends bit packets forged with a fake receiver address, which will be eaten by only eavesdroppers. The detector then sends the memory EMR when the eavesdropper is the bit to memory. To realize this idea, we tackle three key challenges. First, when multiple devices coexist in an environment, their memory EMRs mix in frequency spectrum, making it difficult to accurately sense them separately. Second, despite the amplification of multi-channel architecture, memory EMR is still very weak, requiring an effective way to stimulate eavesdroppers without incurring their notice. Third, memory workloads of operating systems and applications also produce memory EMR. Such EMR is difficult to distinguish from eavesdropper's response, thus may lead to false alarms. To address the first problem, we develop a signal processing algorithm to sense memory EMR based on its spectral characteristics. Specifically, to reduce EMR intensity and meet regulatory requirements, memory systems employ spread spectrum clock, or SSC, which yields a unique spectrum pattern. As modeled in this equation, A memory clock is the sum of a series of subclocks, where the frequency of the first subclock is located as f0, and the interval between consecutive subclocks is fi. The bottom figures show the EMR spectra of DDR3 and DDR4. Agreeing with the model, the energy of memory EMR is distributed as a series of energy peaks, where each peak corresponds to one subclock. Exploiting this spectral feature, we propose a novel use of folding, a computational efficient signal processing algorithm originally used by large radio telescopes to amplify periodic astronomical signals. Given a noisy spectrum, EarFisher folds up the spectrum to search for subclocks. When folding using a window size of fi, the energies of subclock components will be fused, thereby leading to a boosted SNR. After folding, each device will produce an energy peak at a specific f0 and fi. Moreover, due to small manufacturing deviations, different memory clocks have different f0 and fi. This allows EarFisher to separate memory EMR in the two-dimensional space of f0 and fi and track their powers of individual device. To further differentiate memory EMR from other radio signals, EarFisher uses two facts. First, in order to achieve a meaningful data rate, the bandwidth of radio signals is much higher than subclock. Second, the frequency interval between memory subclock is often within a short range, which allows EarFisher to exclude radio signals by specifying a small folding range. However, despite amplification of multi-channel memory, memory EMR is still very weak, which requires a large FFT window to suppress noise. This means that EarFisher must stimulate the eavesdropper for a long period of time in order to trigger a noticeable response. A naive method to realize this is transmitting a large block of bit packets. However, this may block wireless channel and interfere with normal network traffic. In addition, it will introduce an abnormal traffic pattern and thus alert the eavesdropper. To address this challenge, EarFisher splits a large block of bits into a series of short packet bursts and then disguises them as normal network traffic. Specifically, EarFisher disguises these short bursts of bit packets as a session of web page download. This figure shows an eavesdropper's response when it's sniffing on the downloads of 7 web pages. We observe that YouTube triggered the strongest response due to its large page size, suggesting that the stimulator should leverage media-rich pages for stimuli. To further boost the stimulus intensity, EarFisher replaced the traffic of web page downloads in the local network to mitigate round-trip delays, and then bundle multiple bit packages together using frame aggregation to bypass MAC layer contention. To infer if a receiver is responding to stimulus, EarFisher compares the amplitudes of memory EMRs measured in the presence and absence of stimulus, named as stimulus site and baseline site respectively. The stimulus site is measured at the transmission time of bit packets, and the baseline site is measured at other time to sample the EMR produced by normal memory activities. In addition, EarFisher doesn't measure memory EMR when there is ongoing normal network traffic, because otherwise the EMR of legitimate receivers may pollute the baseline site. EarFisher then puts the signals into two large FFT windows. Once both windows are completely filled, EarFisher runs the sensing algorithm to identify and separate memory EMRs. Then, for each device, EarFisher uses hypothesis tests to infer if its memory EMR is statistically higher than normal under stimulus. We implemented a prototype of EarFisher using inexpensive blade RF and conducted experiments on a test bed, where 3 EarFisher nodes are deployed at S1, S2, and S3 in an indoor environment of 1,600 square feet. We then evaluate detection rate and false alarm when eavesdroppers and receiver are placed in 9 different rooms. We found that 8 of 9 DDR3 and 7 of 9 DDR4 eavesdroppers can be detected by at least one EarFisher node, with a recall higher than 93%, while incurring no false alarms. EarFisher detects more DDR3 eavesdroppers because DDR3 memories generally consume more power than DDR4, which leads to higher EMR energy. We note that to further improve detection performance, we can mitigate blind spots, such as room F and G, by extending the coverage of EarFisher by optimizing the deployments of EarFisher nodes. In summary, we presented EarFisher, the first eavesdropper detector that can achieve practical coverage and differentiate eavesdroppers from legitimate receivers. We believe EarFisher prevents an important block of building secure wireless networks. Future steps include localizing and fingerprinting eavesdroppers, further improving the sensitivity of memory EMR, sensing by incorporating advanced signal processing capabilities, and integrating EarFisher security protocols to, for example, verifying the confidentiality of key establishment process. That's the end of my talk. Thanks for listening.